Alright, so the first couple of videos I'm planning to make are not related to our current unit. They actually kind of go back to our epidemiology unit or our microbiology unit. And mainly this is because of our global pandemic with COVID-19 currently going on. A lot of you have probably either been following the news or looked at websites with this whole exponential growth curve. And some of you may have seen this logarithmic graph option. So part of what I'm doing is trying to help you figure out what this stuff means. So I'll kind of go through it. There is going to be a tiny bit of math, but don't worry if you are not super comfortable with math. I will try to bring it down to simpler terms so that you would be able to read these graphs and kind of understand where we're going, what's good, what's bad. I'll show you a website that you can access and we'll go from there. All right, so to understand a bit about how things spread, one of the things you might have seen in a website is something called an RO value. This stands for a reproduction rate. Basically, it is a mathematical value that says how quickly a disease can spread. So from Wikipedia, the source says that for COVID, they believe this reproduction value is 1.4 to 3.9. And what this means for us is, on average, how many people an infected person will spread it to. Now, this is an average value. Some people will spread it more, some people will stay home, and this depends on a number of factors like personal hygiene, how much people are self-isolating. Key idea is the higher this number is, the more contagious or more infectious of a disease this is. So Wikipedia also has several other reproduction rates. For example, influenza has a value of 1.5 to 1.8. If instead we talk about the measles, which was a very infectious disease, one of the videos we said had a 90% chance of catching it. This means that a person who's infected can spread it from anywhere from 12 to 18 other individuals. So very, very infectious. So to show how this works, we'll pretend that every day someone can spread the infection to other people and they will get sick. So at the very start, we have one infected person. Now, what we're going to do is this one infected person is going to infect two other people. So I'm going to do 1 times 2. And that's going to give me 2. So 2 new people are going to get infected. So that brings my total up to 3. Now, the one person, our original person, has already infected 2 new people, so they are done infecting. Maybe they're staying home, maybe they're getting better. But these 2 new people, on average, are going to infect 2 more people each. So these 2 people here, I can use the term 2 times 2 to give me 4 new infections. And then I'm going to add that onto the previous value. So my previous value was 3, so now there are 3 plus 4, so 7 infections. Our new value is 4, so now I have 4 times 2, which gives me 8 infections. I add 8 onto the end and I get up to 15. And very quickly, you'll see that this graph kind of takes a very steep slope upwards. And if I keep going, I'm going to very quickly run out of paper because now I have 8 times 2 is 16. I'm going to go up to 31, and you're going to see it's going to just go off. Now, one of the things, exponential growth curves do not last forever. People who are infected cannot infect other people who are infected. So at the very worst case, we're going to run out of people to infect. The whole population is going to be infected, and this curve is going to flatten out. So at some unknown value, it's going to plateau. But the issue is, how do we know when this is happening? How do we know when we have a disease under control? Because at any one time, we might be here. And it's very hard to tell at this point how close we are to the end. We know what happened before, but we don't know what's happening tomorrow. And another thing that makes this difficult is we have a range of infection values. again, this might depend on any number of things, on what day of the week it is, whether or not the government's putting new things in. So in reality, an infection rate, if I did 1.4, it might be somewhere down here, and then 3.9, it'll be even steeper. So what I actually have is sort of a range showing exponential growth. And the trouble with that is, if we kind of stay within this range, it's very easy to keep growing and growing and growing. So additionally, when we have very, very high numbers like in the US, it's hard to track trends. Maybe there's fewer cases on a Wednesday, but then it might bounce back on Thursday. So how do we know whether or not a country is doing well in getting this under control? How do we know when we are safe? So one of the things we have to help us are things called logarithmic graphs. So right down here is an example of a logarithmic graph. Now, right away, you're going to notice a few things about a logarithmic graph that look very, very, very different. First up, we have the x and the y axis and how the scale changes. If I have 0 in the corner, it goes to 1, like we would expect, and then the next increment, which is the same distance away, is 10, and then 100, and then 1,000. What's happening? They're getting really, really big, but I'm fitting large numbers and on both the x and the y axis. As well, if you look at the spacings within those increments, they get closer and closer the nearer you are to 10, or the next increment, I should say. Now, this graph looks really weird, but what it helps us do is it can change a linear scale like this, where we have an exponential growth curve going up and up and up and up and up, to a linear scale. Any sort of exponential growth on a logarithmic graph will look like a straight line. Now, where this helps us is a lot of countries have the same growth rate because this disease acts similarly in populations around the world. So there is a website I have posted with a world or by country analysis on this logarithmic graph. So I'll go over to that and I'll show you what it is doing. Alright, so here we are at the website that I was talking about. The link is at the top. I'll also post it in the video. Now, what this is a logarithmic graph of COVID-19 in different countries. So you can see China's already up on there because they were the first country to get it. Now, a couple of interesting things. On the x-axis, we don't have the date. We actually have the confirmed cases. So as this video plays, you will see new countries that show up based on which day it is. And the date's listed up here. So total confirmed cases is our x-axis. 10 is down here. 100, 1,000, 10,000, 100,000, and a million. So as we go from left to right, we're going to get more and more cases. And the vertical axis says new confirmed cases in the past week. So this is how much the virus has spread in that country in the past week. So in the first couple of days, they were at roughly about just over 5,000 cases, and they were getting 5,500 new cases a week at this point. So a very fast growth rate. As I click play, it's going to go across the different days. So this is the 1st of January 2020, and it'll go up to yesterday's date, which is April 5th. So as I go, you will see growth, and as it starts to spread to different countries, you'll see them appear down below. So you can just see Canada's appeared, and we go up to yesterday's date. Now, a couple of interesting trends. Because COVID-19 spreads similarly in different countries, it acts the same with different people, all the growth rates look very similar. So unchecked exponential growth is going to fit somewhere along this line. You can see the United States is currently at the top with just about 300,000 to 400,000 cases and 200,000 new cases in the past week. And if I mouse over, it'll give me the exact total. And key idea to take away here is if you are falling along this horizontal or this linear line, that represents an exponential growth. On a regular graph, this would look like our exponential growth curve. So currently, most countries are on there. What a country wants to do is to not be on that line. It wants to be below, which means it's growing at a slower rate. So, for example, South Korea in most recent days, a lot of people have started to recover, but the weekly confirmed cases has gone way down. So they've fallen off of this curve. They're still going up because there's still new people being infected, but the growth rate is what we're concerned with. Same thing with China, it has fallen down. Couple things to be aware of. Logarithmic scales tend to kind of squish everything together. So it's hard to see exact totals. For example, US has 337,000 cases. If I go over to Spain, they have 131,000 cases. Almost 3 times as many, and they're very close together. If I go over to, say, same jump to, say, Iran, or the UK, 48,000. So while this helps us see really big numbers, it also squishes things together. If I switch to linear, it'll spread out the United States quite a bit, but then we run into the issue of all the countries being over here, and it becomes very hard to accurately read what's happening. So a couple things to be aware of. There are a few other really good videos. For example, the video that I got access to this was from Minute Earth. It is a very good 7-minute video on that kind of reiterates a bunch of the points I've made. Additionally, there is 3 Blue 1 Brown. It is a longer video, but it has different simulations of an epidemic and how this actually appears to spread throughout populations. And one of the good things that this one does is it talks about things like social distancing and how that affects the spread. It's a little bit longer. It's not super mathy. I would definitely recommend watching it. And any questions you have, feel free to post in the comments or in our teams, and I'll try to answer to the best of my abilities. As always, stay safe. Take care.